to the Greenwich Museums. It's up at M31. It really blew up a huge controversy. It was bigger than that old presidential debate. It was really a lot of venom flowing back and forth. Some astroimagers loved it and others hated it. The idea was to make a tilt focus device such that while the main subject was focused, it looked like it was floating very nearby. It's one of the Greenwich astro images. Okay, let's get back to the real program here. Returning to our regular program, the full moons are remarkable for this month. Sometimes the moon's further away and sometimes it's closer to us, further away and closer to us. And this month, this one right here and the one underneath the picture, if your picture is the same as mine, the moon is pretty far away. As a result, it's going to be pretty small. The moons vary by about 14% in their size, about the same difference as there is between a quarter and a nickel. Depending on where they are in their where the moon is in its orbit. Now, usually I just tell you about the planets and, oh, I hope this isn't in the way on this particular image. This is another one of the images from Greenwich Museum. And you can see the moon over here. And in the same shot, right back over here, you should be able to see Jupiter. I hope you can. We know the planets can lap each other. And oops, where are we? There we go. We know the planets can lap each other, and as they're lapping each other, you can even see it better if we tilt this up a little bit. You can see that we're all in about the same plane, and that plane is called the ecliptic. Well, the moon is almost in that same plane too. It's only about 5 degrees off from the rest of the solar system, ecliptic. So it also gets in the way of planets. Here is a list. Yoo-hoo. Change slides. Where are we? Here we go. Oh, here's that. Here's the list of where the moon violates social distancing rules to get near other planets in the solar system this month. Last Friday was the best example, not so much for us because it rose a little late for us, but Mars and the moon got together. And here we have a couple of images of that event. The big one here from Augusto Xavier from Brazil, and another was a series of watching Mars where the moon actually got in front of the Mars. So it made for a great picture, but that was already passed. It's we've got a couple of other dates here that you could get planets close together to the moon, but there aren't that many. And as we race around the lanes, we can see that, well, we all go around and around, but there's something really peculiar about it right now. You notice that almost all of the planetary masses are all on one side. Well, will that unbalance the sun? Yeah, as a matter of fact, it will. The very center of the solar system is actually not in the center of the sun, but rather offset from the sun a little bit. Jupiter is pulling it off to the side. And with Jupiter and Saturn over here, Mercury over here, and the other planets not too far from that line, we're all pulling the sun this way right now. If we were on a solar system far away and we were looking back and took enough time, took the care, we would actually see our sun wobbling. And that would be proof that there were planets around this sun. Now, as far as what's up in the news, well, one spooky thing is that recent discoveries say that there may be alien life out there. Now, that headline's a little bit of a stretch from what the scientists actually announced. One study of Mars found subglacial and subsurface water. They used radar to penetrate the surface, and the return signal indicated water. Big news, since many think that water is essential for life. Another study using some 40-year-old data found phosphine gas high in the clouds of Venus. We all know that the surface of Venus is a hellhole. It devours spacecraft with acidic rains and temperatures that can melt lead. But 50 miles up, the temperature on those clouds are rather pleasing, like the Earth was before global warming hit. And that is where the scientists found phosphine gases. And as far as they know, phosphine gases can only be generated by life. So there could be a form of life floating around in the relative cool of the upper atmosphere of Venus. In space exploration news, October 4th through 10th is World Space Week, although from what I could see, the US isn't participating much in this. There are a few things happening, including a crew launch of the ISS, and we have a few satellite launches, including another group of communication satellites, an array going up. They've been showing up in our astro images lately, and we're going to have more of them going up pretty soon. But I think the coolest thing of all that's happening in space exploration this month is that we're going to go to an asteroid and we're going to pick some stuff up from it, and we're going to come on back to Earth with that stuff. On September 8th, 2016, NASA launched the OSIRIS-REx mission to an asteroid called Bennu. Now, Bennu goes between the Earth's orbit and Mars's orbit about like this. This is a diagram of how far away it's getting, and boom, did you see that? At some point, it's going to get so close that it's probably going to run in. It could very well run into the Earth as it goes round and round and round like that. In 2060, it has about a 1 in 2,700 chances of hitting the Earth. That was it right there. See that cute little hit the Earth? Yeah, hope we're around for it. Anyway, after hanging around in orbit, Bennu, are you going to play? There we go. After hanging up there in orbit since December of 2018, the probe is finally ready on October 20th to go fetch a sample of this neighbor. The simulation is based on actual pictures of the asteroid. As you can see, it'll take some pretty accurate flying to hit just the right spot for the sample. It will grab about 60 grams of material and return it to Utah. That's all the more room they've got, just a little bit between two parked cars. The 60 grams of material, incidentally, is about 2/5 of a cup of raisins. That's not much in the way of, there's not much going on. Oops, come on, slide. Next slide. There we go. There's not much going on in the way of comets and meteor showers this month, so we're going to skip straight to deep space observing. The glorious summer Milky Way is setting in the west, and the winter vision has not yet arrived, so we can focus on distant galaxies. We have the prima donnas like M31 over here and M33, the Triangulum galaxy. They're always crowd favorites. And you'll notice that all the shots here are from the OCA website, their image gallery there. Remember, the OCA has one of the premier special interest groups for astroimaging, one of the best in the country, and it's a long history of producing remarkable work. And you can also find their images of groups of galaxies that are worth hunting. Set your sights on Stephan's Quintet or the Diurnal group and see how many of these galaxies you can pick up in your telescope. And there are other challenges. One of them surprisingly more difficult, in my opinion, is the Helix Nebula, here imaged by Joe Bush, who incidentally is my fellow graduate. He's a fellow graduate of Bishop Amat High School and of Claremont Men's College, just like me. Hi, Joe. Although this is the closest planetary to Earth and fairly large, the Helix Nebula is really far south for us, barely rising much above 30 degrees at its highest. And that makes it hard, both visually and photographically. But as Joe's image attests, you can see it, and you can make pictures of it, nice pictures. And it can be even hard for us to do astronomy with this Kofivi thing, keeping us stuck up under the suburban skies. I talked to you last time about the Astronomical League's Urban Club, but look at all these other clubs that they've got that you can be part of. Now that the Kofivi confinement has stretched for so long, maybe you need other ideas for suburban skies. This list of adventures from the Astro League, they're all good from your backyard. The moon, double stars, constellations, all available and educational. They're things that astronomers should do. So go do them. Look it up at the astroleague.org. And remember the advice I had about last week, or the last time I was here, tips from the Urban Club. Try to observe during a new moon if you're going for deep sky stuff. The later, the better. You know, all these pieces of information, you can find them there at the Urban Club. But most of all, it's all in the attitude. You may not get as good a view looking at all these things, but the task of finding them, finding your target, is much more rewarding when you're in town. So go ahead and take it. And that, folks, is what's up for October. I'm done now, and I guess I'm ready to move on to the next phase of my life.
A great presentation, Alex. Thank you very much. Informative and entertaining. Great. Now we can deal better with these spooky times. So next, we have our Commander-in-Chief, Commander Doc, to tell us about the cosmic adventures.
I'll hit my communicator here and say hello to everybody. Nice to see you online again, and hope you're enjoying the meeting. And Alex, that was a stupendous What's Up. And I've heard 30 years worth of What's Ups, and you just do a really good job. Please come back many times and do that. But tonight, right now, we'd like to do a little more introduction to the Cosmic Adventures, not to give you all the details, but to motivate people to go in and sign up and take a look at it. We've organized a set of activities that will help you increase your enjoyment of astronomy. So even if you're one of those people caught in a light polluted area like we are in Long Beach, where there are more airplanes than stars, recently there haven't been as many airplanes, but they're still ahead by a few. The Cosmic Adventures is designed for people like you to move ahead with astronomy and do new things. So to give you some more details, let's turn it back over to Reza.
Thank you, Commander. Okay, to tell you more about all this, let me start by sharing the website. So here we have the OC Astronomers website at ocastronomers.org. If you use the top navigation menu items, go to SIG's special interest groups, the very first item will be Cosmic Adventures. Let's go there. So we have divided this into two portals. The first portal is the imaging portal. And thanks to the partnership we have with the Las Cumbres Observatory, we get to use their global network of 16-inch telescopes. On each, there is a SBIC CCD camera attached. We use softwares like SALSA-J and AstroImage-J to process our images. And to compare notes and results, we share them on Padlet. Now, to show you the Padlet, I have Bonnie here. Bonnie.
Thank you very much. I'm Bonnie Thurber, and I've been working in various kinds of astronomy applications for a lot of years. However, I am not an astronomer. I love looking at the sky. I love looking at the stars. So what I'm sharing with you tonight is, again, Padlet. And this is OCA, OCA's Padlet. So as we look at it, we can see there are some lovely pictures of stars that you've done. And I just wanted to say one of the reasons the reason I like this version of Padlet is because you can easily post an image. You can say a little bit about the image you posted, or it's nice to say why you posted it. So here's M101 Pinwheel Galaxy. If I click on this, I see a larger version of the image. Then I click on the outside of it and I go back to the regular version. And as I was looking at these, I actually, there are places you can make a comment by saying, yes, I love this image. And then you can make a comment, you can ask a question about the galaxy. And as I was going through these tonight, I looked at this image by Andrew Sweetland, and I thought, gee, I love the way he's done this image and the colors are bright. But then I thought, what can he do to make it look even better? So I made a suggestion. I'm not sure if he'll do it or not, but I'd like to hear him say something back. Then I was looking at more of these images, and I saw Emma's Ring Nebula, and I saw, Emma's Ring Nebula, And then this one by Mike. I'm not sure of the last name, but well, actually it looks like it's a email name. And so if you look at the differences here, you can click on the image and see this is what his image looks like. And then you can click on Emma's image and see what Emma's image looks like. And I thought, gee, I started to make some comments on the ring nebulas, and I thought, well, maybe Emma and Mike should have a conversation about their two ring nebulas and why the pictures look the same and why they look different. And then as I moved over to, these just happened to be next to each other, really. The dumbbell nebula, sorry, by Emma. And this one by Ceci, I thought, you know, is it just the way I'm looking at these, or does the coloring look different in these two? So I actually enlarged them to take a look at Emma's. And then I enlarged Ceci's to take a look at hers. And I really think that the coloring looks different, not necessarily because of the filters that are in them, but maybe because of the length of time they took to take the pictures. I'm really not sure. So I thought, well, I could post something on these, but I thought that maybe Emma and Ceci could start talking about their dumbbell nebulas by having a conversation in the comments area. Then I looked down at the rest of them and I thought, there are some pretty amazing things here. And I made a comment here, and I made a comment somewhere on someone else's, and I thought, oh wow, look at this one. I think this is the most yellow or golden I've seen this. So that's from Reza. But and it looks like Anonymous is talking here about how did you get the bright yellow color? And well, Reza needs to go into this and answer that. But you can see here, there's sort of a series of comments here that start a conversation. And while you're in this astronomy club and we're not having, we're not sitting out with our telescopes looking at the stars and commenting there, why not take these pictures and start having discussions about the different objects you take pictures of right here in Padlet? So that's my comment, my sort of presentation about Padlet tonight. It's designed not only to present your work, but to start having comments and collaborations about it. So again, I'm Bonnie Thurber, and I will say thank you for listening to me.
Thank you, Bonnie. Now to show us how it works, we have Ceci with us.
Hi, Ceci here again. And I saw that Bonnie started talking about the Diurnal Nebula, and actually it's not even my image, it's Galileo's, my 8-year-old. So here it is. I know. So over the summer, him and a few kids did a pilot program with Dr. Pennypacker from Berkeley, and he taught them all how to do salsa J, all ages, and this is what they came up with. So here's Galileo's one, Galileo over here again. This was pretty cool from one of our other students over the summer. And everyone here was commenting about the thing here. And I think I loaded 3 or some. Ring Nebula, again, like Emma did earlier, and Mike. Here's Palomas. Right here, Galileo, the Swan Nebula. This is what we did it with Photoshop before we learned how to do Salsa J. And then afterwards, it's right here again, I think, right there. So anyway, I'm looking forward to all of you guys in the club being able to use something. And at first, when the kids were doing it, it seemed kind of like overwhelming because everyone wants to do imaging, right? Well, I mean, I've always wanted to do imaging, especially when I see all of your awesome pictures, but not all of us have the equipment. So this is a way for us to use somebody else's telescope all around the world and be able to produce something pretty spectacular. So welcome to Cosmic Adventures. We're looking forward to seeing your images. Signing out.
Thank you very much, Ceci. Now, if you just go across and travel to the next portal, which would be the citizen science portal, it's for more serious of us. We have asteroid search programs, double star programs, exoplanet finding programs. And to show us a glimpse of how it works, we have Emma with us tonight. Emma?
Hello. So I'm going to share my screen to show you guys Astrometrica.
Yeah, I apologize. I should have called you by Lieutenant Emma.
Yeah. Yeah, get it right. I'm a lieutenant here. But yeah, so this is Astrometrica, which is a program that helps amateur astronomers like you discover asteroids. And what I have here is actual data from the Pan-STARRS Observatory showing stars and possibly asteroids. If I click up at the top of the screen, I can blink the images. So you get kind of a slideshow between the images that I have here. And I can search the images for moving objects. And let's say if I click on this object here, can you guys see the graph yet? All right, awesome. So see how that graph is kind of scattered, the data is kind of everywhere. I'm gonna say that's not a good object. That's probably not an asteroid I've discovered, so I'm gonna hit reject for that one. But if I zoom in and I come down here, if I click on this object, can you guys see the graph? Look at that curve. Look at that data perfectly following that curve. I think that looks pretty good, huh? So I'm going to see if this object is already discovered. And what I'm going to do is I'm going to look at this list of objects I have, and I'm going to see if any of them are within 0.02 arc seconds of the object. And I don't see anything here. Everything is, is not that, isn't exactly or close enough to where this object is. So I'm gonna just hit cancel, and I'm gonna name it myself, because maybe I just discovered an asteroid. I'm gonna call it OCA001, and I'm gonna hit accept. And there it is. Those little pink letters, I don't know if you can see them very well, but there is the object. And I can send this, and as I find more objects and designate more objects, I can send all those in a report to the Isaac people, and maybe I'll get credited with the discovery of an asteroid. It is that simple. Anyway, thank you very much. Hope you enjoy Astrometrica.
Thank you very much, Lieutenant. So now to wrap it all up, we have Chris here telling us about how to join. Chris?
Good evening, everyone. I'm just here with a couple short reminders. So if you go to the Cosmic Adventures page, I'm here to remind you that you must be an OCA member first, which all of us are, so that's checked off. And to register, there's a link right at the bottom. When you click to register, it's free for OCA members, and it will give you a short Google form. You'll fill it out. You'll shortly hear back from our team. It'll give you access to either pathway that you seek to explore. You'll have access to communication streams to gain support. You also have access to tutorial videos, and you'll be on your way to exploring images and or asteroids or whatever it is that you are searching for in the far beyond. So we look forward to you signing up, and thank you for being here with us this evening.
Thank you very much. So now I'm going to the next part of the program. let me salute everybody and welcome you again to the October 9th, 2020 General Meeting of the Orange County Astronomers. I'm Reza, the Vice President of the club, with you here tonight on a stream from the International Space Station. Before we go to the main talk of the program, I would like to bring to your attention the ways in which you can interact with us. First, raising your hand. Please go ahead and find the related button on the middle lower part of your Zoom window and click on that. Great, I'm seeing hands being raised. This is the way we're going to applaud our speaker in a few moments. Second, the chat option. Please use it to send us any comments you may have during the meeting. And third, go ahead and find the Q&A for asking questions. You can use that both during and after the presentation to ask your questions from the speaker. Now, unfortunately, Dr. Marcel Pawlowski, who was supposed to present to us tonight from Germany, sent me a note a few hours ago that he has become symptomatic and would not be able to make it tonight. Our prayers are with him and hope his test results be negative. And hopefully we will have him back talk to us in the future. Luckily for us, though, an old OCAer agreed to jump in on this very short notice. You might know him as president of the Society for Astronomical Sciences, a board member of the American Association of Variable Star Observers, and the author of 2 books for science amateur astronomers. Like many of us, his interest in astronomy started at an early age. There we go. Can everybody see? Can you recognize our main speaker? Excellent. And when he grew up, he did not waste a year to become an OCA member, which he remained for 3 decades, during some of which he served on the board as a trustee and later as the club secretary. His daytime career was in aerospace engineering and management. His nighttime interest is photometry and spectroscopy of variable stars and asteroids. Please join me by raising your virtual hand in welcoming Bob Buckheim from Gold Canyon, Arizona. Bob.
Thank you very much, Reza. And thank you to all of my old friends from OCA and the ANZA observing site, the gang out at 10 Pad Alley. I imagine that some of you are knocking your foreheads and like that little girl in Poltergeist saying, he's back. Glad to be here. And glad to share with you some ideas of things that you can do with the night. Assuming that, there you go, I hit the right button. Our topic this evening is observing the night sky, but in a little bit of a different way than what we normally do. Instead of looking at objects, let's look at events and phenomena, things that happen in the night sky. Learning about things that are happening is a little different than observing and learning about objects. Alex showed a picture of the Andromeda Galaxy. I don't have one that nice. Alex, by the way, if you're taking votes, I love the one with the focus perspective. It really is neat. When we look at this in our telescopes, or maybe in a picture, but since we're observers, we're going to look at it in our eyepieces. And you know, you've been told that by observing this, you're taking a journey through space and time. A journey through space because it is, after all, a galaxy far, far away. And a journey through time because the finite speed of light means it took a long time for the light to get from there to here. But that leaves open the question of how do we know? And it's a little unsatisfying, at least to me, to say, well, I know because I read it in chapter 4 of the textbook. We know these things because before us, some clever people made some critical measurements, and they demonstrated those things that we now know, that the speed of light is finite and how to measure it, and how you determine distances by watching the way a particular type of star changes in brightness. One of the ways to think about the whole history of human progress in understanding the cosmos, the whole history of astronomy, is that at its foundation is a set of seminal observations. People, 2,000, probably 4,000 years ago, they saw the sun rise and set. They saw the planets move. They understood the phenomenon of the seasons. And later on, the parallax of stars and things like that. And it's on those observations and measurements that our current understanding of the universe is based. Well, as I mentioned, a lot of those observations were made a long time ago with really primitive equipment. We now are blessed with telescopes and cameras and computers of remarkable capability and fairly low cost in the big scheme of things. And so that got me to wondering, can I use a modern backyard telescope and an inexpensive modern camera to replicate the observations and measurements that led to the foundation of modern astronomy? All those things that I mentioned. To kind of put myself in the shoes of the great observers and see the universe the way Tycho and Galileo and Leavitt saw it, not knowing what the textbook answer is, but figuring out these things from their observations. And I got to admit, I was gobsmacked when I discovered that all of those seminal observations can be replicated by you in your backyard, even under suburban sky light pollution. And so I'm going to share a few of those steps along the journey to a different kind of understanding of the universe. And one of the many things that I learned in this process of replicating the work of the great observers was that when you actually look at the sky and you make the measurements that they made, the story is maybe a little bit different than the understanding that you get from your textbook. And let me begin with one of the simplest of astronomical phenomena and echo some of the things that Alex talked about the moon in the What's Up session. I think it's part of the 4th grade curriculum in California that the students learn about the phases of the moon. And, we all have at least a vague understanding of what's going on from our everyday experience. That you go out one evening and you see a skinny crescent moon like the one in the upper right in this image, and a few days later you've got a quarter moon overhead, and then the moon keeps getting bigger and bigger, and then over on the left side of the image, a couple of weeks after that thin crescent, the full moon is now rising as the sun is setting. And then the cycle is a little harder to see because you have to stay up a little later at night to get down in the lower left where the full moon shrinks back to a gibbous, and then down at the bottom of the image a third quarter moon, and it gets smaller and smaller, and then back over on the left it is just before dawn, a skinny little crescent, and then it disappears for 3, 4, 5 days where you can't see the moon in the sky at all. Now, you've seen most of that, and you probably believe it when I tell it to you. Your textbook will tell you, as Alex did, that cycle from new moon through crescent to full, back to crescent, and back to new moon is called the lunar month or the synodic month, from the time period from new moon to new moon. And your textbook will tell you that the length of the synodic month is 29.53 days. And if you get that question on your exam, that's what you're supposed to spit back. 29.53 is the answer. On the other hand, how do you figure that out? How do you figure out the time interval from one new moon to the next when you can't see the new moon? You can't observe when it was new as opposed to a skinny crescent. And how do you do that with an accuracy that you can say, well, 29.53 days, not 0.54 or 0.52? 0.01 of a day is about 15 minutes. So you're making this incredibly accurate measurement of something that you fundamentally cannot see. Well, you cannot see it, but if you slip your little digital camera into a small telescope and you make images like this, every night or two, you go through a whole month, you make these series of images. One thing that you can do is turn this vague concept of phase, from new to crescent to quarter, turn that vague concept into a mathematical equation. If the diameter of the exterior circle of the moon's limb, is big D, and the maximum dimension of the illuminated part is little d, and we'll call the phase little d divided by big D. So when it's a full moon, phase equals 1. When it's a new moon, phase equals 0, except you'll never actually get a picture of that. But once you've quantified the concept of phase, you can measure your images, each one in turn, measure the diameter of the moon's image and the size of the illuminated slice of the moon, put that into a little spreadsheet, and you can make a graph of phase versus date. This is data I took quite a while ago. And you can see, you watch the moon rise to full and then fall down to a thin crescent, and then it disappears for a few days, and then it reappears in the evening sky and starts rising up back toward full again on its next monthly cycle. Now, you still can't measure the time of the full moon, but what you can do is take a closer look at the half a dozen data points that bracket the full moon. And if you're a skilled user of Excel, ask the spreadsheet to fit a quadratic curve to those data points. That's the little dotted line on the inset. And a little bit of algebra will tell you the precise bottom of that dotted curve, the precise date and time of the new moon that you can now infer from your measurements, even though you didn't actually see it. And you do that for the first cycle of the new moon, and then again at the second cycle of the new moon, and you can calculate now what the time difference was between the two of them. Interestingly, I think interestingly, when you do that, measure new moon to new moon, you won't get 29.53. Your textbook's not exactly wrong. It's that usually we gloss over some of the subtle details that the textbook tells us. That 29.3 is the average length of a synodic month. The synodic month, new moon to new moon, is not a constant interval of time because, as Alex pointed out, the orbital inclination of the moon's orbit relative to the ecliptic, the changing distance from Earth to moon orbit means that that interval of time from new moon to new moon is different. If I remember right, it differs by about plus or minus 7 hours, a third of a day, which is a pretty sizable difference on something that's 29.53 days. So the world looks a little different in real life when you make the measurements than it does in your textbook. Now, as long as you've made all those pictures of the moon and you made them through the same telescope and the same cameras, so the image scale is identical, and you've measured the diameter of the moon's limb, it's kind of interesting to plot that versus time. How big did the moon's image appear as it went through its cycles of phases? And here's a graph from that same set of data. And as the moon went through its seasons, its phases that month, the size of the lunar image grew and shrank. And it changed by almost 10%. If you were paying really close attention, when Alex slipped by, one of his slides had a picture in the inset of the moon at apogee and perigee, and you just look at it and you can see they are different size because the moon doesn't go around the Earth in a circle. The moon's orbit is elliptical, and so it goes from farther apogee to perigee and back, and you can actually measure that changing size of the moon's image. It's not in sync with the phases. The period of the perigee to perigee time interval is 27.6 days in round numbers. It's about 2 days less than the period from new moon to new moon. So sometimes the moon is largest when it's new, sometimes it's largest when it's full, and in general, the two are uncorrelated. Now, you can do that with your little telescope and little camera, and you can measure it, and then you start to recognize that there's something really complicated about the way the moon moves and the way its phase changes. And doing that with a camera and a telescope and a spreadsheet is a nice little science project, and gives you another insight into how the moon works. Here's a question for discussion over at the party after the meeting. We know this today, and we can measure it pretty easily today. The Babylonians, 3,000 years ago, they knew the time interval from perigee to perigee. It's called the anomalistic month. They knew that. They didn't have computers and cameras. I haven't found any. I can imagine how they might have done it, but I haven't found any evidence of actually how they did it. Anyhow, once you've seen this picture of the moon, getting bigger and smaller, it is awful tempting to remember watching the full moon rise over the ridge on the east and how big it looks and how close, like you could practically reach and touch it. In fact, if you got to the top of that ridge, you could practically jump onto the moon. So it makes you wonder, is this phenomenon what we're seeing that makes the moon appear so large when the full moon rises? And you have now a way to measure that for yourself, to answer the question for yourself. Is this what's going on? And that is, the next time you have a full moon scheduled to rise over that ridge, get your same camera and telescope and take a series of images as the moon rises and eventually passes overhead, and plot the size of the moon image versus its position in the sky. Now, the killjoy teacher will tell you, no, that whole, big full moon, that's an illusion. Because if you think about where you are on the Earth, and there at the top of the picture, and the moon just rising over the horizon, that's when it's off to the left. And then as the evening progresses, the moon rises till it's straight overhead. And if the moon's reasonably circular orbit around the Earth, it's going to be closer when it's overhead than when it's just rising. So take your measurements and check. And it turns out, son of a gun, the moon's image is larger when it's straight overhead, which means it's closer to us, which means in this case, your data seems to validate the picture that your Killjoy teacher told you. Let's go beyond the moon. You probably remember reading in your textbook the story about Tycho and his supernova. Tycho, for any of you who don't remember, was a very famous astronomer of the late 1500s. Late 1500s, meaning the telescope has not been invented yet. So everything he did was naked eye observing and naked eye measurement with kind of glorified theodolites and things like that. And of course, at that time in Europe, the general understanding of the way the world worked is that here on Earth, in the terrestrial realm, we are subject to decay and change and corruption. Up in the sky, in the celestial realm, that's where stability and perfection lies. And it's not a bad example. We see things change and decay all the time here on Earth, but pretty much the cosmos is reliable. The stars will always be there. The sun will always rise and set. So into that, Tycho is the guy who made very precise measurements of the positions and motions of the planets, trying to figure out what was going on there. And so one evening, a new star appears in the sky, what we today would call a supernova. To them, it was just a bright star in the sky. And that presented a serious philosophical issue. If that bright object was maybe somehow related to meteors, it's an atmospheric phenomenon. That's a terrestrial thing. The fact that it changed is no big deal. But if it's in the celestial realm, now something new has appeared in the heavens. That is something that shakes your worldview. As it turned out, 5 years later, he was continuing with his cycle of observations, and a bright comet appeared. Here's another thing, that maybe it's a celestial phenomenon, in which case you shouldn't be seeing changes in the heavens. Maybe it's a terrestrial phenomenon, some kind of an odd cloud or fog, and in which case all is right with the world. In both cases, Tycho recognized that the moon provides a convenient boundary line. Things that are closer to us than the moon, we can assign to the terrestrial realm. Changes are expected. Things that are farther from us than the moon is, that's the celestial realm, and stability and perfection and lack of change is what we expect. And your textbook will tell you the story that Tycho made careful measurements of both of these objects in their days and showed that they were in fact more distant from the Earth than the moon. They were in the celestial realm, which began to put a few cracks in the picture of stability and perfection up there. And there the story stops. Well, how did he know how far away they were? No telescopes, no computers, fairly rudimentary instruments by our standards. Today, if we want to measure the distance to a star, we use parallax. And I think most students run across that concept that the Earth goes around the sun. You measure the angle to a star on this side of the orbit, angle on that side, and you can, a little geometry, you can calculate how far away the star is. Well, turns out you can do that sitting in your backyard with a slight change in concept. Let's say there you are sitting in your backyard. If the screen is a little bit cut off, there you are sitting under the images of the videos on the right side of the Earth. And you make a measurement of, say, the angular position of the moon or the comet or the supernova. And you just sit there in your backyard for 6 or 8 or 12 hours, and the Earth rotates and carries you across a distance of several thousand miles. You now have a baseline that's of the order of the diameter of the Earth. You make another measurement of your object, and you can start to see parallax motion if the object is close enough. And that's part of the key to what Tycho did. He could measure the parallax of the moon. He could not measure the parallax of that supernova or the comet, which proved that they were farther away, hence in the celestial realm. Here's a painting of Tycho in his observatory with really kind of a neat setup with fancy instruments and assistants scrambling around to do his bidding. I wanted to replicate that in my backyard with this stock digital camera and its kit lens, and a 50mm lens on a tripod. And it turns out you can. The challenge is to make pictures of the moon that show it in front of the stars, so you can measure the position of the moon relative to the stars. And also, because the moon obviously moves in its orbit, in addition to showing some parallax, you have to make these measurements on 3 or 4 consecutive nights, so you can unravel what is orbital motion and what is parallax motion. But it turns out that little digital camera, you can measure the distance to the moon to an accuracy of a few percent. Replicating what Tycho did and facing many of the same problems that he did. It turns out the same method, if you put a camera onto a small telescope, in the middle paper here, I think Eduardo used an either 8 or 10-inch telescope in his backyard. You can measure the parallax and the diurnal parallax, and hence the distance to asteroids from your backyard. And even if you're very, very careful, he and I partnered on a project to measure the distance to Pluto, and we succeeded. Now, there's a really important historical aspect to making measurements of the distance, in particular to asteroids. For well into the 1700s, the problem of how large is the Earth's orbit, what's the astronomical unit, was a subject of deep and energetic investigation. And you've heard the stories about, the adventure and romance of the expeditions to go measure the transits of Venus. Fabulous stories, really wonderful adventure. Didn't do that much for astronomy, because of the challenge of measuring. If you've ever made that measurement, you've seen what's it called, the water drop effect. It's really hard to tell when Venus is right on the limb of the sun. But in late 1600s through the middle 1800s, this method of measuring the distance to asteroids, which also go around the sun, was the fundamental and accurate way of measuring the size of the astronomical unit. So with this technique, you now have a way of beginning to put an actual scale in kilometers or miles on the size of the solar system. A major advance in our understanding of the universe. Let's move on to Galileo, a generation after Tycho. The paradigm was still pretty much perfection in the heavens, with a few exceptions like those comets, and the Earth being the center of the universe, because the Lord put the Earth in its place and it shall not move. And Galileo had the advantage of living in the era when the telescope was invented. He himself made pretty dramatic improvements to the design of the telescope. The Copernicus had raised the question of, is the Earth really the center of the universe, or is the sun the center and the Earth go around it? There are some arguments against the Copernicus idea of put the sun at the center. They sort of are, well, it just common sense is, I can tell that I'm sitting still here on planet Earth. And there is darn little observational evidence for anything going around something other than the Earth. We see the moon go around us on a monthly basis. We see the sun appear to go around us every day and in the changing seasons. If the Earth were going around the sun, then we should see a parallax motion of the stars, which we don't. And in Galileo's day, there was no example of anything going around something other than the Earth until that fateful night when he aimed his telescope at Jupiter. And he saw something like this, something like you see when you look at Jupiter. There's the planet, and it is usually accompanied by 1 or 2 or 3 or 4 little dots of light arrayed in a pretty much a straight line to its left or right. Now, we've all looked at this, and most of us have probably told people at a public outreach thing, see, this is what Galileo saw, and he realized that those are moons going around Jupiter. That is jumping a little bit ahead of what he actually did. He looked and saw, and if I remember right, the comment that he made in his notebook that first night was, well, that's odd, in Italian, of course. But if you slip your little digital camera into your telescope and you take a picture of Jupiter and its moons on one particular night, we have the advantage of you can take a picture every hour or so, and you can watch the dance of the moons. And at the end of the first night, put that in your computer database, and then the next night you look and wow, things have changed. They're in a different relative positions, which is exactly what Galileo saw. The second night he looked at Jupiter, he said in Italian, well, that's interesting. The configuration is different, but there's still Jupiter accompanied by these things. And because you're watching over many nights, you can watch Jupiter pass in front of the background stars, but these little companions stay with Jupiter and they continue their dance in the course of night number 2 and then night number 3, and you're gonna kind of get a gut feel that they're moving along with some sort of a pattern, but it's sort of hard to unravel what it is. And you see these sketches just like this in Galileo's notebooks. Now, take your images and measure the distance from Jupiter to each of those 4 little dots that are accompanying it. And don't even worry too much about the angles. They're all pretty much in a straight line. So just measure the distance, pick an orientation. If they're the left of it, it's a positive distance. If it's to the right of Jupiter, it's a negative distance. Just measure them and put them in your spreadsheet and plot what you see. And for those 3 nights that I just showed you in the animation, this is what you'll see. They all look kind of the same, and it's still a little bit of a jumble. But if you add another 2 or 3 or 4 nights to this plot, what you realize is you can connect the dots. And you connect the dots in a very special way. Each of those dashed lines is a sinusoid, a curve of sine times omega t. Now, there's no documented evidence that I'm aware of that Galileo did any calculation or graphing like this. But he was a professor of mathematics, and it's hard to believe that a professor of mathematics didn't understand the relationship between a sine curve and uniform circular motion seen on edge. In any case, he was able to take his observations and realize after several weeks of this observation that yes, indeed, these little dots are going around Jupiter. They are in orbit around it, just like our moon is in orbit around us. That was the first recognition of a center of motion other than planet Earth. And that was earth-shaking. He understood the significance of what he was seeing, and that got him into all that trouble with the Pope, and we won't bother with that here. Interestingly, 9 years after Galileo published his measurements of these little dots going around Jupiter, another interesting observation came along the scene. Kepler was working in Germany. Kepler and Galileo were contemporaries, and they corresponded with each other. So 9 years after Galileo had figured out this business of the moons being in orbit around Jupiter, Kepler published his third law of planetary motion. That's the one that says the period of the orbit squared is proportional to the diameter of the orbit cubed, the one that the high school students always have trouble with. Again, there's no documentary evidence that I am aware of, but I'm confident that when Galileo got the letter from Kepler announcing, p squared is proportional to d cubed, I can just see Galileo, now under house arrest, going over his own notes and realizing that these stars around Jupiter, the stars of Medici, his stars, follow the same law of planetary motion that Mars and Saturn do in their orbits around the sun. Let's move out of this. Reza, I haven't been keeping track of time. How am I doing?
We do have.
I'm sorry, say again.
We have 10 minutes more.
Okay, cool. Thank you. I'll set a timer. Let's go to the stars. Every time I've been at an astronomy club and done a talk, I ask, everybody knows about Algol, the demon star, the eye of the Medusa. It's changing brightness over time. But when I ask how many people have actually seen it, watched it happen, maybe 5% of the audience has actually seen it happen. It's worth doing. And it's another one of those things that your digital camera, no telescope, just its stock 50 millimeter lens, you can repeat what John Goodrich saw when he measured visually Algol's brightness night after night to discover the fact that it was constant brightness for many nights, and then one night it would be dim. Next night it's back to normal. And if you follow that long enough, you can piece together when do the dimmings happen. And it turns out they're on a very regular cycle. Goodrich realized this. This is a copy of his letter to the Royal Society in 1783 announcing this discovery of the periodicity of Algol's dimmings. Interestingly, he's not the only one who was watching the star in 1782 and 83. Very shortly after he published this, wandered onto the scene a letter from a German count reporting to the Royal Society that one of the farmers in his neighborhood had also been watching this star and had determined that the dimmings happen on a regular cycle. And Farmer Pallich got essentially the same identical answer that John Goodricke did. Now, very few students are going to be enticed to repeating Goodricke's observations, going out every night, night after night, making a meticulous visual comparison of how bright is Algol compared to the stars next to it. That's just a little too fiddly, I think, for the average modern student. But you have a little robot who will do the observations for you. Aim it at Algol, go out on a night when Sky and Tell says that there's going to be an eclipse, take an image of Algol and the surrounding stars every 5 minutes or so. And that image, there's Beta Per, that's Algol. And measure the brightness of Algol using your image processing software, and plot Algol's brightness versus time over a few hours that night. And in the image on the left, you see brightness changes a lot. And then when you catch it on the rising end, it rises up back to normal. If you follow Algol for every night for a few weeks, you map out what its brightness looks like outside of eclipse, and you'll see something like this. John Goodricke, who had done that, made a hypothesis that this star Algol is not a single star, that there is a something going around it there, blocking the light from the star. That's the eclipse we see. And interestingly, the idea caught hold very quickly. Everybody said, yeah, that makes sense. That's the paradigm of the times. Things go around other things. Whatever a dark star is, it makes sense that it might go around a regular star. I'm going to leap ahead so as not to impose on the audience. Let's ask, why would you want to do any of these projects? There's a big difference between taking a quick look in an eyepiece or a quick look at a picture versus really seeing what's going on, taking the effort to stare and understand and think about what you're seeing. And it's an even bigger leap of progress to be able to measure what you're seeing, measure what changes from night to night, or even hour to hour. Those measurements are at the heart of modern science, and they form the beginning of understanding of these celestial phenomena that many of us are at least vaguely familiar with. By doing it yourself, you will never again be put in the position of, when someone says, how do you know that? To having to say, well, I read it in the textbook. Instead, you can say, oh yes, I've measured it myself. There was a philosopher who pointed out that there are limits to textbook learning, because the important things that we learn, we don't learn them just through our intellect. We learn them through our experience. And replicating some of these seminal astronomical observations is a way to experience the universe that our grandparents and forefathers experienced, where they didn't know what was happening, but they could see it happen and make measurements and form theories that are the foundation of our modern view of the cosmos. So I encourage you all to, in all of your looking, to try to do a little measuring. And if we have time, I'm happy to try to answer a few questions.
Thank you very much, Bob. It was a very fascinating presentation, and also thank you for doing it in such a short notice.
My pleasure. Oh, yeah, commercial announcement, buy my books.
The floor is open. Please use the Q&A option to send us your questions. We already have some. The very first one, I believe the answer, you would need to put the commercial slide back up. Somebody's asking if there's a published description of how to make these and other seminal observations ourselves, which this would be the answer to it.
Yes, the answer is the book on the right, Astronomical Discoveries You Can Make Too. It is, and I don't remember the exact number, but in round numbers, 35 observational projects that take you from recognizing that the sun rises and sets all the way toward measuring the distance to the Andromeda Galaxy, all in your backyard. Amazon, Springer, the usual places will be happy to send you a copy. And for the those of you in the youth group, in the Cosmic Adventures group, who get excited about researchy projects, a collection of both projects and procedures is in The Sky is Your Laboratory. It's sort of a lab manual for how to measure variable stars, how to measure asteroids, how to measure double stars. And I would be delighted if you bought one and enjoyed it.
Thank you. And just to make it clear, for those observations that are needed to be done over several nights, how important is it for us to make sure that we have the same setup and same setting?
Good question. Keeping everything as identical as possible eliminates a source of potential measurement uncertainty. Things like, remember we talked about the size of the moon's image. You absolutely have to do that project with one telescope and one camera. No changes in instrumentation. If you have to drag the telescope out of the garage and into the driveway every night, that's fine. Although for a lot of these projects, it's simpler to leave the setup in the backyard if you can, and not have to worry about alignment changing and things like that.
Thank you. Okay, next question is, how do you disentangle the parallax and nightly motion of the moon?
Good question. It's described in stultifying detail in the project description and Astronomical Discoveries, but the essence of it is that to recognize that the orbital motion of the moon is almost a constant angular rate over the course of a couple of nights, whereas the parallax motion is a sort of back and forth. As it turns out, you don't see the moon moving back and forth. You see it moving faster and more slowly, faster and more slowly. And so if you make a series of images over the course of those nights, you can actually see that effect. The linear trend is the orbital motion, and then the faster, slower is the parallax motion.
Thank you. Next question is, how many times have you seen the changing in the brightness of the demon star Algol?
I've only done the Algol project once that I remember. But I'll tell you, it is one of the things that got me involved in photometry and spectroscopy of variable stars. Just the fact that you can see a star change in brightness over the course of a night is sort of mind-boggling. And this one is a very easy project. Now, I will encourage you, there is real live new science every time you do that project. If you can make an accurate measurement of the time of minimum light, same kind of thing when I talked about measuring the time of the new moon. The star gets fainter and then brighter, and you plot that curve and figure out exactly, to within plus or minus a fraction of a minute, when was it minimum brightness. It turns out, although the picture of Algol is one star going around another, that system is far more complex. There's at least one other star and maybe some interactions between Algol and its companions. So the eclipses actually don't come like clockwork. The time of minimum light is off of the clock schedule by a few minutes. And the what's called the observed minus calculated diagram is a really complicated thing. So measuring the time of minimum light of Algol is still contributing to a better understanding of that stellar system.
Thank you. And the next questioner wants to figure out the equinoxes and solstices by themselves. So what sky phenomena, what measurements, what accuracy they need to do to figure out the equinox and solstice time of the day correctly without needing to looking up some information beforehand?
Yeah, there's a couple of ways to do it. The most picturesque that is sort of the poor man's replication of the big prehistoric monoliths is if there's a place in your yard or in your house where you have a clean view of the eastern or western horizon. I did this from the backyard deck of my house in California. We had a ridge in the east behind us, and set yet digital camera on a tripod on the deck, and use the stock kit lens and zoom it out to its shortest focal length, its widest field of view, and just leave it up there, and throughout the year take an image just at the titch of dawn, so you can tell where on the horizon is the sun rising. And you will be astounded at how far the sunrise position moves from summer to winter. You know that the sun rises a little northward in the summer and a little southward in the winter, but until you've done it, it's very easy to not realize just how big an angle that is. So that's the easy way. There are a couple of other ways also.
Thank you. And the next questioner asks, for standard distances to the astronomical bodies like the moon, the planets, the sun, etc., who sets the official numbers? Is it NASA?
As in all of science, there is always a measurement uncertainty. There's no such thing as the precise mass of an atom or the precise distance from Earth to Sun, but there are pretty well-established theories nowadays. And I actually don't know where the Book of Astronomical Constants gets those things today. Maybe John Hoot, I think, is in the audience. He might know. But for example, think about what's the distance between Earth and Sun. Well, the Earth's orbit around the Sun is not a perfect circle. It's elliptical, and so that distance changes every day. And as I don't remember if it was Alex or Doug mentioned that the pull of the planets nudges the sun. The sun's not the barycenter of the solar system, so that effect is going on. So the precise distance from Earth to sun right now, it's a different distance tomorrow by a little bit.
Thank you. And I think there are some observatories that are making constant measurements, like the distance between the moon, the laser they beam to the mirror. Yeah. Okay, and next question is, can you elaborate more on how to get the actual numbers off of the observations we make? Is it we have to take images and then use software to measure the difference between the images, or can you elaborate more?
Yeah, if we're talking about brightness changes, I imagine there's two kind of fundamental approaches to that. The first is what's called differential photometry, and it's what astronomers have done ever since Goodrick and still today in studies of variable stars. You get an image that has your target star and one other at least. And your fundamental hypothesis is that other star, your comparison star, is constant unchanging brightness. And so you measure the ratio of the brightness between your target and your comparison. And that's what light curves of Algol, et cetera, are based on. The second thing is, what do I mean by brightness? If you imagine taking a detailed look at the pixels in the image of a single star, each of them is a little box with a number, the ADU counts, and the brightness of the star is measured by the sum of all of those ADU counts minus whatever contribution skylight is making in there. And there's software that'll do that for you. Maxim will do it. AstroArt will do it. I'm not sure about Astrometrica, but it might measure the integrated brightness of target star, comp star, and then you divide one by the other. And if you're feeling really astronomical, you take the logarithm of the ratio, because that heads you toward magnitudes. But is that a sufficient answer, Reza?
Yes, thank you. That was great. And also we have a message from John Hoot on the response to the standard body that determines the official numbers. That's apparently JPL's ephemeris 430, DE 430. You could search it, look it up, JPL ephemeris, and it has all the measurement, the methods of measuring it and the data on it. Excellent. We have a few more seconds. I'm going to wait for a few more seconds if there are any other questions to come in. And if not, we are ready to end this session. Do you have any closing remarks, Bob?
No, thank you very much for inviting me. I've had a good time. I hope some of you have learned something useful, or at least interesting and entertaining. Thank you all. You have a good evening.
Thank you very much, Bob. So before ending this meeting, I would like to mention the upcoming events from the OCA calendar. Next general meeting, as usual, will be on the second Friday of November the 13th at 7:30 p.m. Dr. James Tuttle-Keene from JPL will be talking about NASA's New Horizons mission to Pluto and beyond. The beginners class will be as usual on the first Friday of November on 6 at 7:30 p.m. David Pearson will be teaching us different methods of finding objects in the night sky. Next, Ventura County Astronomical Society's online general meeting will be held by OCA on the third Friday of October, next week, the 16th, at 8:30 p.m. with a talk by Sarah Elizabeth Manolas from JPL. And our open spiral bar, a place to socialize, will be tomorrow, Saturday, October 10th at 10 p.m. And finally, a questionnaire should be already open on your browser window. We would appreciate your time to answer that in order to improve the quality of our meetings. Everybody stay safe and live prosper. Thank you.